The objectives of the Aerospace Safety Program are to verify that SNAP reactor systems meet the specified safety criteria, and thus ensure that adequate nuclear safeguards exist within the SNAP program through the factory-to-launch sequence, which includes handling, transportation, assembly, launch, flight, and re-entry. This progress film describes Phase 1 of the Mechanical and Thermochemical Effects Project. These Phase 1 tests were performed at Holloman Air Force Base, Alamogordo, New Mexico, to simulate the potential hazards that might be encountered by fire, explosion, drop, and impact environments. Mock-up reactors and systems utilizing dummy fuel elements were fabricated for each of these tests. Test number 1 consisted of exposing a mock-up reactor vessel and internals to a deluge of liquid oxygen, called LOX, to simulate conditions that might occur if the missile aborted while still on the launch pad, and the reactor was subjected to a LOX spray from the Atlas fuel tank. The purpose of the test was to measure the effects of a thermal shock created by an abort, and to observe the general behavior of the reactor for evidence of structural failure. There was no physical damage, either external or internal, to the core vessel. The results of this test show that the reactor will not be damaged by a LOX spray or deluge. It will maintain its original configuration. The second test was similar, except that in this test, a liquid sodium-potassium coolant, known as NaC, was exposed to the LOX spray. This was accomplished by firing squibs, which severed the NaC coolant lines leading to and from the reactor vessel. 2 seconds later, the LOX spray was initiated. The purpose of the test was to determine the effect of possible chemical reactions on the reactor vessel and to investigate the possibility of an explosion generated by the LOX-NaC interaction. The reactor vessel was sprayed with LOX for 40 seconds. The LOX quickly froze the NaC in the open pipes. There was no chemical reaction. This condition could occur as a result of a missile abort on the launch pad. There was no physical damage to the reactor vessel as a result of these conditions. In the third test, the reactor vessel was filled with NaC and immersed in a water tank. Shortly after immersion, the NaC was released by purposely rupturing the inlet and outlet pipes with squibs. A violent explosion occurred, which shattered the water tank. During this test, the reactor maintained its original configuration. The rapid loss of water due to the tank rupturing minimized the reaction. It was therefore decided to rerun this test at a later date. At that time, the reaction will be allowed to continue to completion in order to determine whether the core vessel remains undamaged after a sustained reaction. The fire exposure test consisted of exposing a mock-up reactor and reflectors to a high-temperature fire, similar to that which might be expected during and after an abort. 2 Sparrow rocket motors and a butane oxygen burner were utilized as heat sources. The purpose of this test was to observe evidence of structural failure and distortion due to the thermal stress of differential expansion. The temperature obtained was approximately 4,000 degrees Fahrenheit for the first 2.2 seconds, followed by 1,500 degrees Fahrenheit for the next 15 minutes. As a result of the fire, the reflector retaining band failed, and the reflectors were ejected. The separated reflectors were prevented from completely falling away by the test rig. The core itself was undamaged. The purpose of this test was to observe the behavior of the reactor for evidence of structural failure and distortion due to the externally applied pressure that could result from a missile abort explosion. The reactor was suspended 13 feet above 256 pounds of TNT. An overpressure of 415 pounds per square inch with an estimated positive phase pulse duration of 2.8 milliseconds was achieved. The reflectors and reflector mounting assembly were separated from the core by the explosion, but the core remained intact. Although these test conditions may not have matched the range of possible abort environments exactly, the relative strength of the assembly components indicate that the same qualitative result could be expected in a similar abort situation. The next series of tests were impact tests to determine the structural effects and behavior of the reactor core vessel, reactor assembly, and control drums when dropped onto the launching pad from the top of the Atlas Agena missile. A tower facility was utilized to simulate a missile on the launch pad. The test article was dropped from the 100-foot-high tower, nose on, side on, and tail on. The impact velocity was approximately 70 feet per second, the free fall velocity which the article would reach during a fall from the top of the missile. Upon nose impact, the retaining band failed, and all 4 control drums were separated from the reflector assembly. During the tail-on drop test, the retaining bands also failed, and the drums separated from the reactor assembly. All parts were contained within the converter cone, with the exception of 1 control drum. A buckle developed in the transition ring of the reactor vessel. The shell was split in the buckled region. In the side-on test, the retaining band failed, and the reflectors were ejected from the core vessel. After impact, 1 control drum rotated through the in position. Data obtained from the test films indicated, however, that reflector disassembly occurred early enough to prevent any possible nuclear excursion before the generation of large amounts of radioactivity. It is therefore evident that in the case of drum rotation, no radiation hazard would be produced. Although the full inward rotation of 1 or even 2 control drums would not cause reactor operation, further drop tests have been scheduled to accurately determine the time sequence of the reflector disassembly and drum rotation. In this test, a concrete-faced, rocket-powered monorail sled was rammed into the pump end of a stationary reactor reflector test article. This test was conducted to determine the structural effects of a reactor assembly impact onto concrete as a result of a missile abort at high altitudes. The 24 by 24-inch concrete-faced steel-backed target smashed into the reactor assembly at a velocity of 560 feet per second to simulate these conditions. The test article was completely destroyed upon impact, and total dispersal of the reactor parts occurred. The destruction in this test was sufficient to ensure subcriticality under all conceivable circumstances. Water impact tests were also included in the test series. Their purpose was to determine the result of a water impact at terminal velocity. The assembly was mounted on a rocket sled. A target tank of water 8 feet wide, 8 feet high, and 16 feet long, was located at the far end of the track. Just prior to the impact, an arresting device stopped the sled and caused the test article to disengage and contact the tank, approximately 6 feet from the sled. The impact velocities ranged from 428 to 596 feet per second. The configuration studied included head-on, tail-on, and side-on impacts of the reactor reflector assembly, plus a head-on impact of the assembly with the radiation shield in place. In all cases, the reflectors were immediately ejected upon impact. The core vessel sustained varying degrees of damage. In the tail-on impact test, a partial dispersion of the fuel elements resulted. In no instance, however, was the fuel element array sufficiently disturbed to ensure a non-critical configuration if the reactor was immersed in water. The test results indicated that in the case of a missile abort into the ocean, prior to being subjected to re-entry heating, the reactor vessel can remain intact. The effect of re-entry heating on structural integrity, which would result from an abort above 100,000 feet, has yet to be determined. Certain basic conclusions resulted from the Phase 1 tests shown in this progress film. Thermal shock due to a LOX deluge has no appreciable effect on the reactor assembly. Chemical interactions, although violent in the case of the NAC water reaction, probably do not damage the core vessel. Fire. Explosion. Impacts at velocities of 70 feet per second on concrete, and terminal velocity impacts into water at 550 plus feet per second without re-entry heating results in reflector ejection with little or no damage to the core vessel. Impact on concrete at 560 feet per second produced complete disassembly of the reactor. It should be noted that in every test, with the exception of the 560 feet per second concrete impact, the fuel element array did not disassemble as much as would be required to prevent criticality if the reactor were immersed in water. Much meaningful and valuable information was gained by the tests performed at Holloman Air Force Base. The successful completion of the Phase 1 tests added greatly to the aerospace safety program. Many additional tests are planned, including the Phase 2 ground testing program, which will include those additional tests shown to be necessary by the NAC water interaction immersion, drop tests, and earth impacts. The tests included in the Phase 1 and Phase 2 ground series and in the other aerospace safety projects demonstrate the extensive effort that is being expended to ensure that adequate safeguards are provided from the time of shipment from Atomics International to Vandenberg Air Force Base until the nuclear power unit is operating in space.